Hey, linear algebra students, this is Professor Call here. Welcome to Math 206, Spring 2020. I'm filming this lecture in my office. It's maybe a little bit cramped. Hopefully you're able to see everything that's going on the board. Let me know if you have suggestions for changing the lighting. Hopefully I'm not blocking the board because it is a little bit tight in here. It's a crazy quarter. I've never filmed lectures before, so it'll take me a little time to get used to this. But hopefully it comes out all right, and hopefully you're able to learn. It'll be a learning experience for both of us, or for all of us. So let's get started. Our first topic, linear equations. Essentially, everything that we do in this class, in the background, linear equations are going to be involved, right? They're really the sort of the heart of what goes on in linear algebra. So just as a reminder, an equation of the form ax plus by equals c, here where I don't want 0 on the right hand side, so a and b not both 0. If you have an equation of this form, everyone I'm sure has seen this and knows what this defines. It defines a line. So this defines a line in the plane R2. In Calc 3, in Math 143, you generalize this, took it up one dimension, an equation of the form ax plus by plus cz equals d, here where not all a, b, and c are equal to 0. So a, b, and c not all 0. This defines a plane in R3, right? So this is the standard equation of a plane. These two equations right here are examples of linear equations. So what's the main characteristic here? What we have is constant times variable plus constant times variable equals some constant on the right hand side. What we want to do is generalize this now. What we had in the first example, 2 variables. In the second example, we had 3 variables. Now what we'd like to do is define a linear equation in the setting where we have n different variables. Okay. So an equation of the form a1 x1 plus a2 x2 plus plus a sub n x sub n equal to b, right? Where I don't want all of these a sub i's equal to 0. So where not all a sub I equal to 0 is called a linear equation in the variables x1 up through x sub n. Right, so what do we have? The main characteristic of a linear equation then, constant times variable plus constant times variable plus plus constant times variable equal to constant on the left or on the right hand side. Right, so that's an example, or this is the definition then of a linear equation. These constants, the a sub i's, those have a name. Those are called the coefficients. So the a sub I are the coefficients. In the case, now we allow b is just some constant. It's okay for b to be equal to 0. So if b is equal to 0, the equation is homogeneous. So let's do a couple of examples here. So if you have 2x plus 3y equal to 4, what do we have here? Constant times variable plus constant times variable equals constant. Here's an example of a linear equation. In this case, because I only had two variables, I used x and y. When I have a bunch of variables, that's when I'll tend to use the subscripts x1, x2, and so on. If I only have a couple of variables, I'll use x and y. If there's three, I'll probably use x, y, and z. So here's another example. Square root of 2 times x1 plus pi times x2 plus 4 times x3 minus x4 equals 0. Here's another example of a linear equation. In this case, we've got the four variables, x1 up through x sub 4. So each of these is an example of a linear equation. Let me give you a couple of examples of variables that are not, or equations that are not linear. How about 2x squared plus y equals 4? Here's an example. This is not linear, and the reason, in this case, we've got constant times variable squared. The key aspect of a linear equation, each of the variables is raised to the first power. Right? As soon as you see squared, it's not linear. Another example, so how about this? Cosine of x plus sine of y equals 3. It's a totally legitimate equation, but it is not a linear equation because we've got cosine applied to this variable, we've got sine applied to this variable. Right? Definitely not. And one more example, let's say square root of x plus 3y equals z. Not linear. What's the problem right here? Square root of x, that throws things off. So here's examples. These are not linear. Now, what we're going to deal with most of the time are what are called linear systems. So, a finite collection of linear equations is called a linear system, or if you really want to get fancy, a system of linear equations. So most of the time, I'll just use the words linear system, right? But it's interchangeable with these words here, system of linear equations. So for example, 2x plus 3y equals 1, 4x minus y equals 0. Here's an example of a system of linear equations. Here we've got two variables for each, right? And we've got two equations. Another example, x1 minus x2 plus 3x3 equals 1. 4x1 plus x2 plus 7x3 equals 0. X1 minus 4x2 plus x3 equals 0. All right, here's another example of a linear system. Now, one thing to point out, yes, I have three variables and three equations. That's not necessary. If I would have just done this and done the three variables and two equations, that's still an example of a linear system. Right? So the number of equations does not have to match the number of variables to be a linear system. Now, what I want to do is write down the general form of a linear system, And in this case, what we'll have is m equations and n variables. Right? So the general format will look like this. So now I'm going to need to use double subscripts for my coefficients. So my first equation, a11 x1 plus a12 x2 plus dot 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 plus a1n xn equals b1. Now I'm using double subscripts, right? I'm about to write some more equations down, but what's going on here? The 1, the first subscript here, says that it's the coefficient in the first equation. The second subscript tells me which variable it's attached to. So for example, a12 means it is the second variable in the first equation. There's going to be an a21 x1 plus a22 x2 plus dot 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 plus a2n xn equals b sub 2. And we can keep going until we get to the very last, the mth equation. A m1 x1 plus a m2 x2 plus dot 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 plus a mn xn equals b sub n. So the coefficients, let's write this down. A typical coefficient is going to be of the form a sub ij, right? The first subscript tells you which equation it belongs to. So for example, in the first equation, all of the variables, or all the coefficients, have as a first subscript, they have a 1. In the second equation, all the subscripts have a 2. In the mth equation, all of the subscripts, the first subscript is an m. The second one tells them which position or which variable it's attached to. So then this coefficient right here would appear as, or it would appear in the ith equation in the jth position. Right, so this right here is the generic form for a linear system, and to avoid having to write it constantly, put a star here. When I refer to star, I'm referring to that linear equation right there. Now, once you have a linear system, what we'll want to do then is figure out what the solutions are. Now, what does it mean to be a solution? It will be a collection of numbers so that when we substitute in for the variables, it actually solves each one of the equations simultaneously. So let's write that down. So a solution to star, to our linear system, is a sequence of numbers, let's say S1, S2, up to S of n, so that when you substitute each of those SI's in for the XI's, it satisfies the equation. Where substituting S sub I equal to X sub I solves each equation. And it's important, it's got to solve each one of the equations simultaneously. We'll typically write the solution, so the notation for a solution will be S1, S2, dot, 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 up through S of n, enclosed in parentheses. This is called an n-tuple. Right. So, for example, here's my linear system, x1 plus x2 plus x3 plus x4 equals 1. And 2x1 minus x2 minus 3x3 plus x4 equals 0. So here's a linear system, and you can check 1, minus 1, 1, 0 is a solution. So how do you verify that? You take 1, plug it in for x1, minus 1, plug it in for x2, 1, plug it in for x3, 0, plug it in. And if you notice, it definitely satisfies the first equation. Also, if we plug it in for the second one, we would have, what would we have? 2, then plug in a minus 1 here. That's going to give us positive 3. Subtract off 3, add 0, equals 0, right? So this is a solution to our system because this right here, when substituted into each equation, gives us a solution to the equation. Now, here's an important fact. For any linear system, right, of the form star, there are 3 possibilities. So one of these 3 has to happen. First possibility, star has exactly 1 solution. So there's one option. Second, star has no solutions. And then part C, star has infinitely many solutions. So if you have a linear system, exactly one of these is going to occur. Either we'll have exactly 1 solution, or we'll have no solutions, or we'll have infinitely many solutions. The important thing to get here is that you cannot have a linear system that has 3 solutions, or a linear system that has 7 solutions. It either has 1 or infinitely many. If it has at least 1 solution, so either A or C, then we say it's consistent. So if star has at least 1 solution, meaning either A or C occurs, then star is consistent. If not, so otherwise, star is inconsistent. So no solutions means inconsistent. 1 solution or infinitely many solutions means consistent. Okay, so that's a good place to stop for now. That's it.